in the supermarket, the direct air reclaim doesn't do quite as well as the water source heat pump. And a lot of that had to do with, this is looking at both heating and refrigeration energy. So this is kind of a total of the refrigeration and energy layered on top of it. If we're spending a lot of additional energy in auxiliary heat, which we don't necessarily need to do, or we're spending a lot more on refrigeration, then it's going to show up as a total. So the water source heat pump, especially on the supermarket where we're closer to parity with our loads, we need a lot less auxiliary heat, is what we found. So it was significantly better than everything except the air source heat pump, where the air source heat pump, we're bringing in air or heat from the outdoors. And when we looked at that, we got much better efficiencies, and that was coupled with the direct air heat reclaim.
Welcome to the Refrigeration Mentor podcast. I'm your host, Trevor Matthews. And once again, always trying to find people from around the world to share their knowledge. And once again, I have my good friend, Patenaude from Copeland here, and Trevor Jones from Henderson Engineering. Both of them are refrigeration professionals who care about sharing knowledge, helping the industry grow. And we're going to be diving into heat reclaim potential for retail space heating. So if you're listening on the podcast, you might have to listen to it a couple of times. You know, if you're watching on the YouTube channel, just pay close attention. Always, as I say in all the shows that I do, is take notes, because this is important. You know, write it down, writing it down again, because there's going to be a lot of information that we share, especially every time I do it. I've done dozens of podcasts with them, I'm sure. There's just so much knowledge being shared. You can't absorb it all in one listen or one watch. So you might have to go back and watch this again. As always, like it, share it, comment it on the different platforms you're on, because this is how more people find out about content like this to really get them to the next level. Trevor, what I would love you to do is do a quick introduction about who you are and a little bit about your role at Henderson Engineers.
Okay, Trevor Jones. I've been in the HVAC/R industry for almost 25 years. Mechanical engineer.
Okay.
I started more on the HVAC plumbing design side, and then moved over to refrigeration. So I have a lot of knowledge on the heating side, especially.
And so you do a lot of design work. So that's it, because you're an engineer background. So you designed a lot of hydronic systems maybe, or just heating systems in general. Like what kind of systems have you designed in the past? Because that's your role, right?
Yeah, heating systems for things like grocery stores,
okay,
which tend to be more like gas-fired rooftop units,
okay, yep,
sitting on the roof.
I worked on tons of those, so I know all about them. And right now in Canada here, it's like -10 or -20 out with the windshield. So I know all about it. I know all about it. So awesome. So Andre, most of my followers know who you are, but do a quick introduction of yourself.
Sure. Thanks, Trevor. Patenaude. I'm the Director of Solution Strategy with Copeland. It's a business development role that has a lot to do with accelerating sustainable strategies, a lot CO2. We've had many conversations, Trevor, around CO2. Also, get involved with a lot of the regulatory stuff, a lot of the stewardship, industry events, presentations, stuff like podcasts, and working with customers and internal folks on decarbonization and sustainable solutions.
Yeah, no, I love
always
that.
Fun.
Yeah, and definitely go check it. Just go onto the Refrigeration Mentor podcast and then search a channel. Just write Andre in. You'll see a ton of CO2 ones that we did there. We did one on CO2 Experts a few weeks ago. It's a couple months now, I think, on the high pressure valve. But you want to go listen to that. You know what I mean? Because it's going to help grow your CO2 knowledge. Today, we're going to get into heat reclaim strategies. And this is what I talk about in our CO2 trainings all the time, if it's the intro or even the advanced, because this is not new. 20 years ago, when I was in the technician in the field, I was working on heat reclaim systems here in Canada because we use them a lot here, but it's not used as much around the world since CO2s came. And I've seen more and more talk about heat reclaim since CO2 comes into the retail space than ever before. And I don't know if you guys noticed this as well, Trevor or Andre, but heat reclaim, heat recovery strategies are huge because over the last 30 years, we've been just shooting a lot of that out to the atmosphere, right? Condenser just shooting all the heat out, where now we can really use that heat. And I think this is some of the stuff we're going to dive into today.
Yeah, no, you're absolutely right, Trevor. And one of the things that in preparing for this session, trying to figure out, how is this material relevant to your audience? The refrigeration technician you talked about, and the common theme that came around was this is addressing a mega trend, that's happening around not just moving to low GWP refrigerants like CO2, but it's also trying to decarbonize the grid and move away from fossil fuels. To your point, there's been a lot of heat reclaim in Canada, maybe in colder areas, but how can we look at this study is to look at, how can we really have the data to be able to continue to talk and decarbonize based on energy and reducing overall carbon footprint. So that's what we're going to try to share today.
Yeah, I love that. And this is a big thing in our training programs too. Like the technicians come in, it's like, why does this matter to me, Trevor? Like we're doing trainings and, it's a 4 or 6 week program. Why does like decarbonization matter? Or why does, all the sustainability stuff matter? But when we talk about carbon reduction, and even if some people want to dive in deeper, I talk about it. It's not only the refrigeration system efficiency, but it's also the planet. We're jamming a lot more heat into the planet, you know what I mean? And by reducing or by reusing that energy somewhere else, we're not just running compressors and costing more money, because our background's compressors. That's why I know compressors really well, right? And then if we're just running them all the time, but not using that energy, it's just a cost to everybody, the end user, the grid, the people, and this costs the industry money, and as we call it, it's like a tax. And so in those programs, talking to technicians, the value is that it's going to help your customer out at the end of the day. Because we're always working out there, the technicians out there to work for the customer and trying to bring them the most value. And when you can bring them more value, technicians are always going to have work with them. That's what I say. So this is why it's good and important to understand how we can help that retailer.
Yeah, exactly. If Trevor, if you go to the next slide, it kind of talks about why really Henderson Engineers and Copeland got together and wanted to do this study. So we started this about 2 years ago. And we really wanted to understand what is the real energy and embedded carbon. When you compare, the common refrigeration that you were talking about, that heat reclaim has been around for a while, for supermarket and hypermarkets. So we'll take a look at what size of those hypermarkets they are. So that's number one. The other thing we really wanted to understand as both companies, because we hadn't done the study individually, so that's why we came together. We want to understand how this implementation of heat reclaim can further promote the transition to CO2, because there's a lot of CO2 systems going in, but now if we can layer in the value of space heating, not just from reclaim, but other strategies on top of heat reclaim, when you can't get enough out of that system, what does that look like? And that could accelerate the use of CO2 systems in the future. So that's really why we did that.
Yeah, no, that's very important. So for new listeners, when you talk about, can you kind of explain the carbon, embedded carbon comparison? Because some people will say, what do you mean, Trevor, when you're talking about carbon? What does that really mean? How does that affect us? Do you want to just kind of give a quick explanation of what that is? When people say, oh, we want to reduce our carbon footprint, and you just kind of give an example of that?
Yeah, so this slide here talks about what most of us are involved in on a day-to-day basis, right? We have refrigerant leaks, and we know that those leaks are carbon emissions. That's why we have to move to lower GWP refrigerants. But not just that, the on-site combustion to heat the hot water, to heat the space, to cook food within the food retail space, that's all considered emissions and scope 1 emissions. The next ones are scope 2, that really is around the power. So if you don't have solar, if you don't have wind, you don't have sustainable power, there's an emissions factor that gets played into that equation to provide electrical energy. So we have to count that. And then the third thing in this study was supply chain leaks of moving that fuel to a space. Now, there's a lot more things involved in scope 3, but for the purpose of this study, we use supply chain leaks. Anything else to add, Trevor?
No, that covers it. Some of this data is taken from like the US EPA and general leakage rates, but also looking at how dirty grids are in various locations, because that does vary.
Right. And what do you mean by that, dirty grids?
Are like wind and renewables a large percentage of grid power, or do they have a lot of coal and gas-fired plants? That would be basically how dirty the grid is.
Yeah, so using coal fire versus using a cleaner energy like wind or tidal or solar. Okay, I get you.
Yeah.
Yep.
So those are the emissions that we looked at. Now, when we compare, the next slide kind of talks a little bit about what we compared from refrigeration. Now, we looked at a supermarket, 57,000 square feet, and a hypermarket, which is like 3.5 times larger. So the heating requirements are quite different. And even the refrigeration requirements you'll take a look at, they're also different. And we wanted to take a look at climates from a cold Minneapolis all the way to a hot Miami and everything in between. So we didn't look at every city in the US, but those are representative. And then the architecture we looked at, I think everyone's familiar with 448. These are scroll packs with enhanced vapor injection. So we took an efficient HFC pack and compared it to CO2 booster with adiabatic. And one of the reasons we just took adiabatic, we said, look, many retailers are using adiabatic, so let's not complicate things and do dry and adiabatic. We'll just use adiabatic across the board. And then Trevor will talk a little bit more after on the specifics of the 3 types of space heating that were used. So we use no reclaim with standalone gas-fired rooftop units. Very common, right?
Yep.
Or water source heat pump with an electric boiler. And then we looked at water reclaim. He's going to explain with water source heat pump, electric boiler. And then the last one tied to CO2 system, which is really interesting, is direct air reclaim. So that is reclaiming the heat off the refrigeration system, whatever free heat's available, and whatever you don't have enough, you need to supplement it with something else. Resistance, heat, and or air source heat pump. Yeah. So those are the technologies we looked at.
Yeah, great. And these aren't new technologies. Like everything that I'm looking here, you know, a water reclaim is basically I've seen this on racks before where we're taking and you get the big thermostor tanks. And this was 15, 20 years ago. And you're preheating water. You know, this is with HFC systems, but when we know now you can get a lot more heat out of CO2 versus 404, for an example, per pound per BTU. You know what I mean? So this is the advantage of CO2. And then direct air reclaim. I've seen that 20 years ago as well. So like this is not new, but we know that CO2, there's more taxes to CO2, especially in hotter climates. But the advantage is that we get a lot more heat out of that. We can get more hot water or hot air out of it. And we talked about this many times too, Andre, is that as the years continue on, we got more competition, we got more manufacturers building components, and which is good, which is bringing the prices down. And you've seen this, you've been in the industry long enough. You've seen these transitions, Andre, even back in the 502 and R12 days, that's one switch there. It costs more up front, but as the technology evolves, the prices start to come down. And this is what's happening, I see, with CO2 right now. And I know a lot of people around the world are seeing the same thing.
And we wanted to understand, Trevor, the combination of these technologies, which one is the best from an energy, but also the best from a from the embedded carbon perspective, lowering your carbon emissions. So that's why we wanted to look at this.
Yeah.
And the next slide talks a little bit more about the specifics of the systems. Now, no, they actually, sorry about that, the energy assumptions. With all modeling, this is a modeling study, we kind of drew the line at a 55-degree ambient. Anything below 55-degree ambient, we assumed required space heating. And when you look at those 6 regions or cities, you can see Minneapolis down on the bottom left there, the dark solid blue line. There's a lot of time that it's spent in below 55 degrees, Chicago as well, even some Portland.
Sounds
But
like
as you
Ontario
move
here.
into LA, Miami, not a lot of heating requirements, right?
Yeah.
So that's one thing to understand. The chart on the right, you may have seen this if you use product selection software from Copeland. It's a design load for refrigeration, and we all know that as it gets colder outside, our design load starts to drop. So you can see at around 40-degree ambient, our design load has dropped significantly. So we factored that into our calculations. So our loads are dropping. That means the total heat or rejection available is proportionately dropped. So we can't heat as much, but that's okay. We factored that in so we can understand how much free heat we have available. Okay, that was part of it. So the next one, really now we're looking at architectures. A lot of us on the audience kind of get the system on the left for a supermarket and a hypermarket, a medium temp with EVI, enhanced vapor injection. So you're providing some subcooling of the liquid, medium temp and low temp. You can see at the bottom our assumptions for 448 medium temp, TD on the condenser 15 degrees. On the hot summer day, we've got, winter, we've got a minimum 70-degree condensing. In the winter, we'd see about 60-degree liquid. In the hot summer, we get about 75-degree liquid. So that's for medium temp. And low temp, you can see the numbers there, 10-degree TD, 65 minimum, so on. And my booster, we've got our minimum condensing set at 60 Fahrenheit with 5 degrees subcooling and a 36-degree flash tank. So that's kind of the basic setup, and the capacities will build now. Next slide, please. So what we see is supermarket, because these are 448 packs, they're smaller. So we got 4 racks for supermarket and only 1 CO2 centralized plant, if you will, for the CO2. You can see 258,000 BTU low temp for the supermarket and 474,000 BTU medium temp. When you get, though, to the hypermarket, you'll notice something interesting. The low temp loads are almost the same. They're slightly greater than a supermarket, but your medium temp loads are significantly larger. And now that creates a dynamic that you're going to see later on, that supermarket, when we look at total percentage of low temp load to total system load, is 35%. And hypermarket is only 29. If we look at the CO2 system, for example, when I've got 35% of my total low temp load discharging into the medium temp suction, that has an impact on efficiency, because now your whole medium temp compressors have to manage 35% of the total system load coming from the low temp. I bring this up because when you look at energy numbers later, it'll have an impact. Next slide.
And that makes sense, because now, as we know, and like I talk about, and you'll learn in taking CO2 trainings, is that discharge of that low temp goes right into the medium temp of the suction. So you got to really understand that. And this, when you're doing hot gas defrost, which we're not going to get into and stuff like that, but that there's penalties there that go back into that you need to make sure that you consider. And this is all done as a technician. You don't really need to understand a lot of this. This is the designers, like what Trevor does, and the manufacturers of the equipment that work for the retailers. But it's something that you want to understand, because the more load that you got to come there is going to affect what happens on the medium temp side, and then that all goes back to an amount of energy that that unit uses.
No, you're right. So conceptually, you may have a service tech that has access to energy numbers in one store. And it might look like the same footprint as another store down the street, but the energy might be higher because that store has more low temp load to total.
Exactly.
So understanding that, you may go, now I get it. Now it makes sense why it's a little bit higher. So that's something that we saw come out of the numbers when we were doing the study. Of course, we all know that CO2 is very efficient in low ambient, but in high ambient, that's why we added a gas cooler to try to keep the pressures as low as possible. So the next slide, please. So the adiabatic, what's interesting here is we understand adiabatics are used to keep it in subcritical as long as possible. And if you can build again, please, Trevor.
Yep.
Applying adiabatic in this particular study, we turn the water on at anything over 72-degree ambient. The water would start to trickle onto these pads. And what's interesting, when you look at Los Angeles from a city all the way down to Miami, the percent runtime in supercritical using weather data from NREL, National Renewable Energy Labs, TMY3. This is the data, temperature data we used. It showed that the water only came on 5% of the year. So 5% out of 8,760 hours a year. And it used 45,000 gallons for a supermarket and 113 gallons for a hypermarket. And you can go all the way down the line here because water is a resource that we have to track and we have to understand it. And that's part of our calculation. What was also interesting is the stat at the bottom from the EPA, which I thought was kind of cool, that an average American household consumes about 30,000 gallons of water per person. So a family affords 120,000 gallons a year, which is about what a hypermarket in Los Angeles uses, quote unquote. Kind of gives you, something to compare against, which I thought was kind of cool.
Yeah, I haven't heard that, but that's interesting when we think about what we do on a daily basis,
Right.
So especially here in North America or in Canada where we got lots of water, but this is different to places in the world where they don't have a lot of water. And even in North America, there's lots of places that don't have a lot of water and there's restrictions. So, and we talked about this before, Andre, that adiabatic is not always the solution. It might be a good solution, but it might cost you more because of that water situation.
No, you're right. In some applications, some region of the world, think about using gray water, filtering gray water, and just using that for maybe not 72-degree ambient, maybe it's above 85 degrees just to trim peaks. So different strategies in different parts of the world trying to leverage some efficiency where possible.
Yep. Awesome.
So the next slide shows, I believe, it's energy. Well, this is interesting. So supermarket, energy only without heat reclaim in this case. Trevor will be talking about layer in heat reclaim, but this was interesting because you take Minneapolis at the very bottom left, the dark black line is 448 with EVI, the blue is CO2, and you can see that CO2, a little bit of an energy advantage with adiabatic gas cooler in every region except Los Angeles. CO2 is a little bit higher. In Miami, a little bit higher. Remembering that the percentage of low temp loads was 29% of the total load for supermarkets. Now, if we layer in the next one, hypermarket, very interesting because we had less low temp load. And look at the impact, how more energy efficient CO2 is across the board, even in Miami.
So if you're listening, just a second. So if you're listening to this and you're not looking at these charts that Andre and Trevor are showing, is actually the annual energy uses of these systems. And this is, I don't know, it's not surprising to me, but it's showing that in a lot of applications using the HFC refrigerants with EVI, which makes systems more efficient, are still using more energy as a baseline. And the funny thing is, I was talking with a friend of mine, Ian Toon, out of Australia, and he was telling me, all the baselines, the data theory is showing that CO2 is way more expensive theoretically in all the design work. But what he's been seeing after 7 or 8 years of the systems running, they're running way more efficient than what the calculators have been saying. So the CO2 systems are running way more because they baselined it and they did all these studies. But when they actually looked at the MMV, the measurement and verification, CO2 has been a lot more energy efficient than people have been saying.
If
I
we
don't know
take
if
the
you
time to
noticed the
set them
same
up,
thing.
no, you're right, Trevor. If we take the time to set them up properly, commission them properly, and have the right, depending on where you are in the world, of course, you have to have the right mitigation strategies to take advantage of it. And this particular set of data was only one mitigation strategy. It was only adiabatic gas cooler. There's nothing else from a high ambient perspective, and there's nothing else from a low side energy saving strategies. So that was interesting to us. And if Trevor builds the next slide, the reason being here that the hypermarkets took advantage of the fact that there was lower low temp loads to total. So that was interesting to see the big difference when we went through the data.
It's interesting to me to see because I get these questions all the time in our training, in our design programs. People ask like, Trevor, we're going to start designing CO2 systems. Does CO2 actually cost more to run? And you're showing data here that it's using less energy in a comparable system. But like you said earlier, it all depends. What is those high ambient strategies? What is the location around the world? How is it set up and fine-tuned by that contractor? How do the end users want the maintenance? So there's a lot that goes involved. But do you know what doesn't change? It's no different than what it should have been done 20 years ago. You know what I mean?
No, you're right.
Absolutely. I've seen so many case studies when we work together, Andre, where we're showing a 20-year-old supermarket where the contractor went in, you work with the contractor, Andre, and they went in and just fine-tuned the store. And they got like 15, 16% efficiency gain or 18% on some of the old store. That's just by doing maintenance on it. And it's a similar thing. Now we're more conscious about our energy, and the retailers are, because power is going up. So now consistent fine tuning and monitoring is going to be key. And what's great about CO2, we got so many temperatures and pressure probes that we can do it more accurately now than ever before.
You're right. The problem in the past has been holding the gains. Once you do it, the challenge is how do we hold those gains and don't allow it to keep drifting back to where it was pre-recommissioning. And you're right, with all the electronics, it gives us visibility and can send alarms and notifications when things get out of whack. So we are at a place with electronics, a better place to be able to hold those gains once we've achieved them.
Yeah. And just remember, retailers who are listening out there, it costs money to save money. And what does that mean? That you got to pay the contractors and the people to go and make sure it's fine-tuned properly, and not let your store just run off. Oh, well, we'll just do it. We'll be reactive instead of proactive. You got to have people take a look at it. This costs money, but if you do it right, it's going to save you money over the long term.
Yep. I think, Trevor, you're up, if I'm not mistaken.
Yep. This is my side. The space heating systems. So we, Andre mentioned that we looked at systems without heat reclaim. So refrigeration system and roughly a rooftop unit, gas-fired rooftop unit, where we're looking at 67-degree return air temperature, a minimum supply air temperature of 85 degrees. And that was kind of the set point. Looking at gas-fired standard efficiencies, 80% AFUE. So that's what we were going by. And we also looked at, without reclaim, the water source heat pump system. And this is a very simplified water source heat pump schematic, where you'll have a boiler, a fluid cooler for rejecting heat, boiler to add heat, and a water source heat pump that's just moving heat in and out of the loop as needed.
Yeah, it's pretty normal. This is not anything new. If you worked on some of these before or worked on a supermarket that has them, there's lots of them out there. So it's
Yeah. So adding water source heat or heat reclaim to the water source heat pump, reclaim heat exchanger. We're looking at a loop temperature of roughly 60 degrees, which that keeps the condensing temperature of CO2 or the refrigerant low, basically at minimum. And the efficiencies of the water source heat pump at that range are roughly 4. You can get a little bit better, but that was a nice round number.
and this right now is talking about the 448 system, correct?
We actually I looked at it for both the 448 and our CO 744, so CO2.
Okay.
So yeah, this is what the system was looking like. And then expanding to the direct air reclaim, again, we're now bypassing around the condenser gas cooler and a straight heating coil in the unit. We initially looked at it with electric resistance heat, and then we also looked at it with an air source heat pump component.
Okay. And so what was the difference that between those two different options?
With the air source heat pumps are far more efficient in introducing heat to the building. And I'm kind of being careful with how I describe them. They're not creating heat, they're introducing heat to the building from the outdoors. So you're cooling the outdoors to heat your building.
Yep.
So I will note on the hypermarket, we were looking at a system that used 100% outside air through large air handling units. So we were basically preheating the incoming outside air in the hypermarket scenario. In the supermarket scenario, we were using return air and outdoor air and then heating that up. So kind of looking at, these are the loads based on ambient temperatures. So of course, it's kind of easy to see the heating loads are gonna be a lot higher when it's colder and then reduce as it gets warmer. And also, our hypermarket needs a lot more heat than the supermarket.
Oh yeah, bigger store, bigger area to heat, and lots more water. You know what I mean? You got more bathrooms if you're doing preheating. You got more the bigger meat rooms, and so that we totally understand that it's going to need a lot more. And as always, like we had a lot of these conversations before. In the middle of summer, when you don't need heat, it's really hot outside. That's when you get the most. You get the most energy that you can use. Now it's in the middle of the winter when we need the heat. We don't have as much because we're more efficient today. We got all glass doors. We got curtains on everything. Our buildings are more efficient than before. The newer buildings, the insulation. So we know that it's a bigger struggle to get that heat out of any system. It doesn't matter if it's CO2 or 448. It's just we just don't have. They're more efficient. So we're not just creating as much heat from that compressor.
That's right. And so one of the things, or looking at this, the supermarket, we're kind of at a balance point at around 20 degrees where there's almost enough heat to cover the heating load from just reclaim. If we're looking at our hypermarket, you're almost at around 55 degrees. So a lot more supplemental heat was going into the hypermarket design.
Yeah. So really what you mean there is that the compressors that are running at 20 degrees Fahrenheit or -6 Celsius, that's the ambient outside, you're only generating about half that heat through the heat reclaim. So we need the other 50% through some sort of heat, auxiliary heat, correct?
Correct.
Okay.
Now, one thing is the available heat off of the system, it remains fairly flat in the coldest periods because you're running down at towards your minimums.
That's right. Yep. Because that high pressure valve is maintaining a certain temperature and pressure in that gas cooler. So that's all you have of whatever heat that is. So whatever that high pressure valve's doing. Okay, fantastic.
Yep. And now looking at some of the total energy use. So right off, you can see there's a big penalty in not using any of the reclaimed heat significantly, and that's for each location.
Well, it makes sense. We're just throwing that heat away, right? So we're building it, we're creating heat, and then we're just throwing it out the gas cooler or the condenser, depending on the applications.
So those are the two systems we've looked at. Now, when we start looking at reclaim, in the supermarket, the direct air reclaim doesn't do quite as well as the water source heat pump. And a lot of that had to do with the fact that this is looking at both heating and refrigeration energy. So this is kind of a total of the refrigeration and energy layered on top of it. So if we're spending a lot of additional energy in auxiliary heat, which we don't necessarily need to do, or we're spending a lot more on refrigeration, then it's going to show up as a total. So the water source heat pump, especially on the supermarket where we're closer to parity with our loads, we need a lot less auxiliary heat, is what we found. So it was significantly better than everything except the air source heat pump, where air source heat pump, we're bringing in air or heat from the outdoors. And when we looked at that, we got much better efficiencies, and that was coupled with the direct air heat reclaim.
The funny thing is, Trevor, you're showing all these graphs and consistently see on here that CO2 is using less energy than the 448 system.
Yeah, their amount of heating energy, the amount of reclaim that you can get is actually really close between the two. So what you're seeing there is the slight difference in energy efficiency of the systems, of the refrigeration systems when we're pulling that heat out.
Yeah. And that's the big thing we know. And like I said, I talk about this in our CO2 training programs all the time. CO2 just has more heat. You can use it. You get more heat out of CO2 than most refrigerants. And this is why space heating with CO2 is going to continue to grow. And I see it more and more happening. Water reclaim and heat reclaim happening on so many racks out there. And the startups I've been to, it's just going to be something that if you haven't been using it, you're going to get used to, because you're going to see more and more of these.
Yeah, what we refer to it as is the quality of the heat. It's hotter, and hot heat is easier to make use of than more mild heat. So if it's it's a difference between if it's 180 degrees or is it only 120 degrees.
Yeah,
it's easier to use that 180 degree heat than it is the 120 degree.
It is worth noting this study did not take into consideration hot water heat. This is only space heating. So we did draw the line there. And to Trevor's point, high quality heat's great for heating hot water, but we didn't take that into consideration for this study.
Yeah, no, and that's fine. But it's just for people to understand that you're getting good heat from CO2.
Right, 100%.
We also didn't include heat storage,
right?
Either like ground source or anything like that.
That would be a 2-day talk, Trevor. That'll be a
that would, we wanted to get it done.
Maybe phase 2. Yeah.
Yeah. So the hypermarket, when we looked at that, so again, we see that big penalty for no reclaim. But then when we start looking at water source versus direct, it kind of evens out because we need so much additional heat anyway that there isn't a huge benefit for the water source heat pump with no storage. So if you have some way of storing heat, like injecting it into the ground in the summertime, yeah, this might change, but that's a little bit of a different system.
Yeah.
There are still some areas where water source heat pump shows a bit benefit, but those are in more mild climates like Dallas and Portland, where you don't have that very cold days that we're trying to provide the additional heat for. And then again, the air source heat pumps, it looks even better with the hypermarket design than in the supermarket because there's so much additional auxiliary heat that we're going to need.
Yeah.
So when kind of looking at direct air reclaim and air source heat pumps, so when it's really cold air, direct reclaim does very well. As the temperature of the outside air increases, there's a point where the amount of heat that you're really getting off of the coil starts dropping because you're not going to be able to heat the air up beyond a certain point. Now, with TCO2, there are ways to adjust that, but with air source heat pumps, they typically have very poor efficiencies when it's really cold, to the point where most manufacturers have a lower limit that at that point you're just running either pure electric heat. There are some new dual fuel heat pumps that are basically your standard heat pump, but instead of electric heat, they use gas. So one thing we looked at was pushing the pressures on our CO2 systems above minimum to see if we could get a little more heat. So that actually came back with a slightly interesting answer, and it kind of depends. One of the things is you have to be able to use all of the additional heat that the system is producing. If you don't, then you're not fully condensing. And if you don't get by fully condensing, you keep your mass flow for the system fairly low because a compressor is not a great way to generate heat. It's good for moving heat, but it's really not as efficient as, say, an electric resistance heater for generating heat from electric power, if that makes sense.
Well, they're refrigeration compressors, usually not heating compressors, right? So you're right, moving heat, and we're just trying to use that extra energy that's created because it has to be created so we can cool stuff, we can pull heat out of stuff. So the whole purpose of it is to use that heat that's generated anyway, right? To be more efficient with the way we do things.
Yeah.
As we were working through this study, Trevor, we've heard that all you got to do is keep running the head pressure just above critical point, and you're going to get all kinds of extra heat. Well, Trevor is going to talk about maybe not always.
You will get extra heat.
Right. You will get extra heat.
But what's the cost?
Yes. What is the cost? So we looked at it both for the water source heat pump and the direct reclaim, whether or not it made sense to push your head pressures higher. And looking at the water source heat pump, there's actually a little energy penalty. So it actually costs you more. You do get more heat, but you're spending more power to get that heat.
Yeah. Makes sense.
Now, when we looked at the direct air reclaim, there's more because there's just more usable heat. We're more dependent on the temperature difference with direct reclaim. Then you actually can still save a little bit more energy. But interestingly enough, going into the transcritical, and some of this actually had to do with the system architecture we were looking at. What we saw was going up a little bit was better than going all the way up to transcritical. Now, that was just for the systems we were looking at.
Yeah.
On other systems, yeah, you'd want to go to transcritical. That'll be your best energy point. But it might not always be. So that's going to need to be looked at into. Where do we want to run things?
Well, it's like anything. It's how much energy are we going to use to get the BTUs we need, either in cooling or heating? So it's, or how can we reduce that amount of work on those compressors at the end of the day?
Yeah.
If we can shut off those compressors, man, we're saving some energy. But we need those compressors to run for cooling and heating. So there's a fine balance there.
Yeah. And of course, we threw in the air source heat pump because it's always just looks so good. So this goes back into looking at the operational carbon. So some of our carbon assumptions for direct emissions, we looked at the GWP 1387 for R448A, 1 for CO2.
And GWP, GWP for everyone there is global warming potential.
Yeah.
And CO2 R744 is 1, and then everything else is based off that. Ammonia is 0, I believe, and propane is 3. So just so those people everyone understands GWP. And I'm sure if they listen to podcasts, I've talked about it before, but it's always good to put it in.
Yeah. So going by some of the EPA data, we assumed a refrigerant leak rate of 25% for both systems. So equivalent
which is astronomically high for today. Like we should be shooting for 0%. We know that doesn't happen. 25 is still way too high. So if you have a system out there that's leaking this much, you got to go fix those leaks. If you're out there, you got to stop it because it shouldn't be that high. It's not a Schrader cap. It's something else leaking. Just spend the time and talk to your customer about this. Is that you got to stop these rates? 25% is way too high for me. So I know you're assuming 25%, but that's still way too high for our industry.
And some leakage may actually be due to improper documentation of service. If you pull off 10 pounds and don't log it, so you're reclaiming 10 pounds to do a service, and you put it back in, or you have to, and then you recharge, and you log that you put 10 pounds in, but you didn't, that you pulled some out first, that would look like a leak in the documentation.
And you should be logging this. I was doing it 20 years ago, logging my refrigerant when I was adding. So anybody listening out there, you got to be tracking this stuff. This is important for your customer, especially when you're doing grocery store or supermarket. We're talking about hundreds to thousands of pounds of refrigerant. You got to be logging that stuff. It's just part of our job as being a refrigeration professional.
And with coming regulations, at least in the US, logging what is pulled out is going to be important as well.
Yeah.
So there's some color coding in how we showed stuff. So we're showing emissions as a hatched light green, and direct emissions for combustion is yellow. So yellow is basically natural gas emissions or emission contributions in following charts. Electrical indirect is blue for refrigeration, and its electrical indirect is orange for the heating systems. And that goes to the total carbon footprint. And this is for the supermarket, what we were seeing. So our baseline with with good heat reclaim, carbon emissions of roughly 1/4, and water source, heat pump, and direct air source, the carbon emissions are very close. So some of that, if you're looking from a carbon perspective, now you might be looking at, okay, which system is going to be simpler overall, easier maintenance, lower cost? Because looking at the carbon, they're effectively equivalent. And some of the locations, one of the things we looked at was direct air reclaim only, or desuperheating only, where we're only capturing a very small portion, because LA and Miami, you really don't need a lot of heat.
So from all this, Trevor, you're showing me all these graphs and what's your recommendation from the study for because this is the supermarket one. We'll get into the hypermarket, but what do you think from this study? Because this is theoretical. This is not M&V and monitor and all this stuff and maintenance and install and service and all that stuff that goes into play. What is from your study here? What's your recommendation for?
If I'm going to recommend to a client which kind of system they should be putting in, I'm pretty much going to be going with direct reclaim and CO2, because with air source heat pumps for the remainder, that way you're getting the best efficiency in your heating mode with the air source heat pumps. For the majority of the United States, there's a lot of hours where the heat pumps will do much of the work and you won't need a lot of supplemental heat. It's not something that's been used a lot throughout the US. There are some places like California where it's pretty common at this point, though.
Okay, let's check out the hypermarket would be the next one, right?
Yeah. And again, we see here it's a little bit different because the water source heat pump needs so much additional heating energy inputted that the air source heat pump, especially in the colder climes, really shines. In the milder climes, they're a lot closer. When you look at Dallas and Portland, the water source heat pump seems to make up ground, but the air source is so much better.
Yeah. Oh, that's fantastic. So for that one there, you would have the same recommendation? And once again, this all comes down to location, climate, elevation. There's a lot of factors that go involved in it. It's not just like you just pick one and it's the same one for everywhere, right? Because there's going to be different components. There's going to be different strategies. You're going to have different quality of skills in that area. So these are all things you got to think about. So it's not one size fits all, for sure, especially this day and age, for energy efficiency.
And these assumed that it was basically a standalone building. If you were looking at a supermarket going into the lower levels of a multi-story building, that's going to be different.
Yeah, for sure.
Now we're looking at, we've got a lot more heat than we're probably going to need. So is that something you could functionally sell back to the building owner for other tenants?
Oh yeah, there's so many factors too that people. So you have a store that you have 20 times more people coming through every day versus a store that has just a small amount of people coming through each day. There's so many factors that's involved. So once again, this is, at the end of the day, if you really want the numbers, it's MNV of measurement and verification of every ounce of energy on all the different components, which is not easy. Because it costs a lot of money to do that.
No, you're right. And one of the things as we talk through all the different scenarios and building types and heat loads, at the end of the day, you got to consult with an expert in that field, right? Guys like Henderson that do this, they make sure that they optimize the right balance point and the right technology for the right building and climate. Those are things. So it's not one paintbrush does it all. So
for sure. That's what I tell our students in our CO2 design course when they're designing. So when you go to a customer, you can't just give them one solution, because maybe they can't afford that a solution, or maybe they don't have the skill level for that. So you got to come up with 2 to 3 solutions that's going to best work for them. Because at the end of the day, because we see more and more adiabatic, I see tons of adiabatic gas coolers going out there. But the problem is the total cost of ownership for it is more, because in your location, you got very bad water. You need more filters. You're by an airport and it's really dirty. So they got to be changed way more than a place that isn't dirty. So when you look at the total cost of ownership and that maintenance, it's not worth it. So this is why you got to go in with multiple options. I keep telling the students, just don't give one option, look at the numbers, break it down, and then do it a second time. Look at the numbers again, because that's probably what Trevor does. You know what I mean? You do all the numbers and then let's make sure these numbers are accurate, and let's test it against something else.
Yeah. Are we looking at some other high or low side efficiency that allows you to get away from the adiabatic gas coolers? Because yes, they are a maintenance issue. It's ongoing. You've got to protect those pipes from freezing. It's water on the roof. And how well does the client deal with water cooling systems? And if they're good, if they have a good technician base and service personnel, they may be, this is easy.
Yeah.
Otherwise, that might be a real lift for them. So staying clear of that can be a good thing.
Yeah, and this is another thing I tell technicians that are in my service and maintenance program is like, okay, you got an adiabatic gas cooler in the middle of the winter, you don't need the water. So the water is going to be isolated. What do you do with that pads? You got to take them out. You know what I mean? You don't just leave them in there and the element's going to beat them up. They're going to last longer. But then it comes down to storage, where you're going to locate them and put them in, because now in 6-8 months a year here in Canada, where it's winter all the time, you don't need the pads even in there. You know what I mean? So these are things that the end user as well as the contractor need to understand. Can you take them out and things like that to make them last longer?
Time that you would operate transcritically is something that really needs to be checked, because that may be we're probably only going to do it a few times, for a couple hours a day. Is it worth it to just spend the extra power at that point and have a simpler heat rejection strategy?
Yep. Yeah, exactly. And this is why I tell all the designers that you got to look at it. What's the value of that total? And Andre, we talked about this tons of time. Total cost of ownership. And this is the problem with some end users, though. It's like, well, it's the CapEx cost. I don't need to worry about, this is our capital cost, the upfront cost versus operation for the next 20 years. And then they don't, hey, that's a different budget. Let's not worry about that right now. And I'm sure, Trevor, you deal with this all the time. It's like, if you work together a little bit more over the grand scheme of things, you're going to save more money when you work together than being in silos of them. And it's just another whole podcast we could talk about, I'm sure.
Yep.
Awesome. Any final thoughts for the study? Andre, I'll go with you. Trevor, I'll go with you for any final thoughts on this study. The biggest things that you took away from spending 2 years on this project.
So looking at how much heat you can get out and picking the best point, so some of it is deciding which heat recovery path you're going to go after. Are you going to go for just preheating all your outside air, or are you going to try and use it for space heating direct? There are reasons to go either way, but then how to do that most efficiently. And some of that TCO2, R448A, that doesn't matter. It's like, okay, how's the best way to get the heat from the rack into your store or back into your store?
Yeah. Right. And I like that. And one of the things I took away is that 25% assumption leak rate, we got to get that down. We want people to assume it's only 10%, 25% is too high. Andre, what's your final thoughts in the study? Because I know you've been involved in tons of study. You spend a lot of time on this. What are some of your final thoughts?
Yeah, I mean, there's a lot of people involved in this study with both companies, of course. It wasn't just Trevor and I,
Yeah.
obviously. But to me, what bubbled out the most was that you just can't assume that you can do the same thing for every store in every location and every store type. When we started working through the numbers and just the percentage of low temp loads to total, it was like, whoa. Yeah, we knew that that makes sense, but now we're looking at the numbers, it makes a whole lot of sense. And of course, we looked at adiabatic versus HFC non-adiabatic. So you do have to factor that in. You have to look at everything when you're doing a comparison. And in order to have the right information, you've got to reach out to the right people that can provide you with information and confidence, so that when you do apply a system in a specific region with a specific technology, you can feel confident that you'll get what you expect. That you're not just being led down a garden path because they did it 5 states over or 5 provinces over and it's going to work here. No, you have to look at it individually for that site and everything else involved.
That's funny that you say that, because I've had quite a few people that took our CO2 design cars and say, Trevor, I'm talking with the manufacturer. They're telling us one thing of the CO2 unit. I talk with the engineering firm. They're telling me a totally different thing of the unit. So I'm taking your program so I can understand both points, because I don't know if they're right or wrong, and I need to understand for myself. And that's where education, training, and development comes into play.
Well, Trevor, you're bringing up a great point, because that's why we've done 4 studies ourselves, Copeland, because we don't want to rely on someone else to tell us. So that's why we did the climate study, this study on CO2 heat reclaim, the ultra low superheat, the total cost of ownership. If you don't do it yourself, then you can't understand it firsthand, and you can't provide the right information to your customer. So that's why we invest and spend time and partner with industry professionals like that.
Yeah, no, I love it. How can people find out more about this study, find out more about you guys if they want to learn more about this?
Trevor put up the QR code on your screen here. If you take your camera and you take a photo of that, it will bring you right to this white paper explaining everything that Trevor and I just talked about.
And if you're if they're listening on the podcast, I'll put the link in the podcast in the description so they can grab the link from there.
And from Copeland's perspective, anyone interested in more information, you can go to Copeland E360 Resource Hub. There's a ton of stuff there on CO2, ammonia, R290, A2Ls from a Copeland perspective. And Trevor, I'll let you talk about your side.
Yeah, how can people find out more about you, Trevor, and Henderson Engineers?
So Henderson Engineers does have a website. Let's see.
Yeah, if they search it, it's Henderson Engineers, they'll find it on Google.
We're an engineering firm. We work with our clients, and we typically are going after our clients are owners typically. So awesome. A lot of our marketing, and one of the reasons the framing of this white paper and presentation, a lot of it's going after that owner market or segment.
Perfect. So if you're listening to this and you want to learn more, check out that white paper, review it. But once again, at the end of the day, is diving in deeper to have a better understanding of how this all works, because refrigeration is ever evolving. The thermodynamics do not change. From 100 years ago, refrigeration to today in 2025, thermodynamics doesn't change. We're moving heat, and there's different ways to do it. Today, though, we're trying to do it more efficiently and effectively. And this all comes back to the design, to the installation, to the service, to the troubleshooting. So you need to invest in yourself to learn all that. And I'm a better technician today because of all the design and engineering work I've been doing in the background to really understand the system, all the different controls, all the different mechanical components. They're new, but we're doing the same thing. We're just moving energy. I want to thank you guys for taking the time to share this white study with us, this white paper, and really learned a few things here, which I like seeing that there's different things being done out there all around the world. You know what I mean? And this here, it doesn't matter where you're listening from, you may see stuff like this. So I recommend reading that, learning more, growing your knowledge. If you like this, share this podcast, the YouTube show, comment on it. Let us know what you thought. Are you doing this type of work out there right now? Are you working on systems that have a lot of heat reclaim, heat recovery with CO2 system? Love the conversation, guys. I want to thank you so much, Andre, Trevor, for taking the time to do this. And as always, join us when you can, because we love sharing this knowledge. My name is Trevor Matthews. Let's get a conversation going. Thank you so much, guys.